Hello. If you've already seen my video illustrating radioactive decay using my dice, that will have demonstrated that the amount of radioactivity remaining falls exponentially with time. But you will have noticed in that illustration that the numbers that we got didn't fit perfectly on the curve. They tended to oscillate above and below the average curve. And that's because this is a random process, and so it has random fluctuations. And so this little illustration is going to demonstrate how big those random fluctuations are. Now, if we take a radioactive source and we measure how many counts, how many radioactive decays we get from it in a given time, we expect a particular number, and if we repeat the experiment, we expect to get a similar but not quite the same number. Now, of course, it might be a bit less because the source has decayed in that time, but even if we allow for that, it turns out that we never get exactly the same number. It varies above and below the expected value. And we call that counting statistics because it shows us how much variation there is in our counts. And the nice thing about the counting statistics is that we can predict exactly how big they should be, because we know they follow a distribution called the Poisson distribution. Nothing whatever to do with fish. It's named after the Frenchman Simeon Poisson, who first investigated this distribution. And the nice thing about the Poisson distribution is that it applies in any situation where you've got a large number of things, like a large number of atoms, and each one's got a very small probability of decaying in any time. And it tells you, in those circumstances, the variation in the number that you get, we call it the standard deviation in statistics, the variation is equal to the square root of the average number that you get. And that's a very nice way of predicting how big the variation's going to be. Now, in the case of radioactive atoms, the Poisson distribution applies exactly because we have a very large number of atoms, each with a very small probability of decaying. With my dice, there's only a chance of 1 in 6 that we throw a 6, and so it represents a decay. So the Poisson's distribution doesn't quite apply perfectly, but it's near enough to illustrate the point. So in my case of my demonstrating radioactive decay, I started with 100 dice. But for this demonstration, I'm going to take 4 dice out, so we've got just 96 dice to make the arithmetic a bit easier. So if we throw these dice, we'll see how many 6s we get. Right, there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, there's another one, 21. And I think that's it. 21. So I'll record 21 6s this time. Now, you may say that's more than the 16 that we expected, but as I say, sometimes it's going to be greater and sometimes less. So I'm going to repeat this, but I'm putting all the 6s back in again, so we top the radioactivity back up to what it was before. We've compensated for any decay. We're still throwing 96 dice this time. So let's do it again and see how many 6s we get this time. So, count again. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, and I think that's it, 17. So 17 sixes this time. We put those back and we try again. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, I think that's it, 16. We record 16 sixes. We put those back and do it again. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, that's it, 14. That time there are 14 sixes. And put those back and once more. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, and I think that's it, 15. Put those back and one more time. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and that's it, just 13 this time. Put those back. How many this time? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that looks like 13 again. 13 sixes. Let's throw again. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, that looks like all of them, 19. 19 sixes. Let's put those back. And again. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. That's it, 18. 18 sixes. And one more time. One, 2, 3, 4, 5, 6, 7, 8, 9, 'Yes, I think that's all. There were only 9 that time. So we've now done that 10 times, so let's see what the results look like. Now we can record our results as a graph. I've got here a histogram showing the number of occurrences of each number of sixes against the number of sixes. The first time we had 21 sixes, which is in the range of 21 to 23, so we can shade in that block. The next time we had 17 sixes, which is in the range 15 to 17, so we shade that one in. Then we had 16, which is again in the range 15 to 17. Then we had 14, which is down here. Then a 15, which is in this range. And then a 13, another 13, a 19 in the range of 18 to 20, an 18 in that range again, and then a 9. So you see we've got a distribution of number of sixes following that sort of pattern, and from that we can see what the average or the mean value was. We expect it to be 16 because it's a sixth of 96, which is indeed right in the middle of the range here for our distribution. But we can do better than that because we know this should be a Poisson distribution, and for a Poisson distribution the standard deviation is equal to the square root of the average. Here the average or mean was 16, the square root of 16 is 4, because 4 times 4 is 16. So we expect a standard deviation of 4, which means 4 above the average. 16 plus 4 is 20, so that would take us all the way up to here. 16 minus 4 is 12, that takes us all the way down to there. So this is the sort of range we'd expect for a standard deviation above or below the average. And we can see that most of our results are in that range. But in fact, it's not unusual to get results that are up to 2 standard deviations away, above or below the mean. And you can see, in fact, all our results are within 2 standard deviations above or below the mean, which ties in with what we expect from the Poisson distribution. So I hope that little demonstration illustrates the nature of random fluctuations when we throw the same number of dice. We don't always get exactly the same number of sixes. It can vary above and below the expected value. And exactly the same thing happens with radioactive atoms. When we measure a source of radioactivity, even if the activity of the source stays exactly the same, we still get a variation in the number of counts that we get in a given time because of these random fluctuations. The radioactivity is a random process in these atoms. We never get exactly the same answer. We get an average value and it varies above and below that. But we can predict the amount of variation from the Poisson distribution because the square root of the average is the fluctuation that we get about the average. And although that's only approximate for the dice, it's a very good, precise measurement for the large number of atoms that we have in any radioactive source.